Welcome to Submodule 3 of 4 on Drillstring Design. In this submodule, we will concentrate on the fundamentals of drillstring design. Drill strings are subjected to intense mechanical loads, including torsion, tension, and bending, as well as fatigue cycles caused by continuous rotation and changes in well trajectory. To design an effective drill string, engineers must balance structural strength, flexibility, and operational performance. We begin by addressing fatigue, one of the primary causes of drill string failure. Fatigue develops from repeated stress cycles, and a well-designed string must minimize these risks by using proper material selection and monitoring stress concentrations. Next, we focus on bending stresses, which arise when the drill string negotiates curvature, particularly in directional wells. Understanding bending stresses is essential for preventing localized overstressing and failure. The module then introduces two critical design parameters, the bending strength ratio BSR and the stiffness ratio SR. BSR helps evaluate the resistance of connections to bending stresses, while SR measures the relative flexibility between drill string sections. Both ratios are indispensable in predicting performance under downhole conditions. We then turn to bottom hole assemblies and how their design controls trajectory. The type of BHA chosen, whether for vertical, build, or hold sections, dictates drilling efficiency and directional control. Alongside this, we examine how weight on bit changes with inclination angle and how indices such as the curvature index CI and stability index SI help optimize performance. Fatigue design is about predicting and preventing failure caused by cyclic stresses. Every rotation in a curved wellbore subjects the drill string to alternating loads. Over time, this weakens the steel until cracks form. In this section, we introduce fatigue and why it must be addressed during drill string design. Fatigue in drill strings occurs when steel is subjected to repeated cycles of stress that eventually weaken the material. Unlike a single overload event, fatigue is a silent process that develops over time, often without obvious warning until failure occurs. In rotary drilling, the primary source of cyclic stress is curvature in the wellbore. As the drill string rotates, any curved section is repeatedly bent, creating alternating tensile and compressive forces with every revolution. These loads are proportional to the severity of the curve, which means doglegs or tight build sections significantly increase fatigue risk. Buckling is another contributor. When axial loads exceed a critical limit, the drill string bows within the wellbore. With rotation, these bends generate additional cycles of stress that further shorten component life. Vibrations also play a role, particularly torsional stick slip and lateral whirl, which introduce irregular and sometimes extreme stress fluctuations. Finally, corrosion accelerates fatigue by reducing steel strength and allowing cracks to propagate more quickly. When combined, these factors mean fatigue damage accumulates silently until sudden failure occurs. Understanding the causes is therefore the first step toward designing a drill string that can endure the demanding environment of drilling operations. The objective of fatigue design is not simply to prevent every possible failure, but to manage risks so that the drill string can perform reliably within the expected life of a well. The first aim is to optimize hole curvature by planning realistic doglegs that the string can safely tolerate. We reduce unnecessary stress exposure. Closely linked to this is the goal of minimizing localized stress concentration points, such as sharp changes in geometry at tool joints or poor machining at thread roots. Another key objective is avoiding buckling. Even small degrees of buckling, once combined with rotation, can impose damaging cyclic loads. By carefully matching weight on bit, stabilizer placement, and hole angle, we reduce the likelihood of instability. Stability itself can be quantified using indices, which provide comparative guidance when designing drill strings for different well profiles. Fatigue design also considers the chemical environment. Corrosive drilling muds accelerate crack growth, meaning it is essential to select proper fluid formulations and to monitor corrosion rates throughout operations. In practice, fatigue design means balancing mechanical, operational, and chemical factors to ensure the drill string remains structurally sound over the planned drilling program. Bending stresses are an inevitable part of drill string operations, particularly in deviated and directional wells. When a straight tubular element is forced into a curved trajectory, the outer side of the curve is subjected to tensile stresses, while the inner side experiences compression. With rotation, these stresses alternate, producing cyclic loading that drives fatigue. The level of bending stress is directly linked to the degree of curvature. A gentle bend spreads the stress over a longer section, while sharp doglegs concentrate it in a much smaller region. This explains why even minor changes in wellbore trajectory, if abrupt, can significantly weaken the drill string over time. Tool joints and threaded connections are especially vulnerable. Their geometric transitions create stress concentration factors, which amplify local stresses beyond what a simple beam model would predict. Properly designed connections mitigate this, but poor matching or wear at shoulders can cause premature failure. The bending strength ratio, or BSR, is a way of comparing how strong the box and the pin are when they are subjected to bending loads. To calculate it, we look at the section modulus of each part. The section modulus is simply a measure of how resistant a shape is to bending based on its outer and inner dimensions. For the box, the outer diameter and the thickness of the steel wall are the controlling factors. A larger outside diameter or a thicker box wall increases its section modulus, which makes the box stronger in bending. For the pin, the effective wall thickness depends on the pitch diameter of the threads, the thread height, and the amount of root truncation. If the threads cut too deep, or if the root is not properly truncated, the pin becomes weaker. Taper and pin length also matter because they define how the load is distributed along the threaded connection. The BSR is simply the box strength compared to the pin strength. If the ratio is less than 1, the pin is weaker and will take most of the stress, leading to fatigue cracks. If the ratio is greater than 1, the load is shared more evenly, which gives us a stronger, longer-lasting connection. Continuing with the calculation, the BSR applies specifically to drill collar connections, which are the most vulnerable components under bending loads. Connections have inherent geometric discontinuities, thread roots, shoulders, and changes in diameter. These act as stress concentrators where fatigue cracks are most likely to initiate. For this reason, BSR is not just a theoretical concept, but a practical tool for connection selection. When evaluating connections, engineers calculate the section modulus of both the box and the pin. The ratio of these moduli gives the BSR. Ideally, the box and pin should have balanced strengths to avoid one side dominating the stress response. A mismatch creates uneven stress distribution and accelerates fatigue damage. Industry practice has established recommended ranges for BSR values that serve as guidelines for connection selection. These ranges are not arbitrary, but based on decades of field experience and laboratory testing. For typical operations, a BSR greater than 1 is preferred, meaning the box is at least as strong as the pin. This ensures that stresses are not concentrated excessively on the pin, which is more prone to fatigue cracking. In high deviation wells or environments with severe bending stresses, operators may seek BSR values substantially higher than 1. This additional margin reduces the risk of premature connection failures and extends the service life of the drill string. Conversely, BSR values below 1 should be avoided wherever possible, as they indicate a weak connection design that is more likely to fail under cyclic bending. The table compares traditional BSR ranges versus the recommended BSR range from DS1. What this shows is that in hole sizes less than 6 inches and between 6 inches and 10 inches and 7 7/8 inch, the recommendations are consistent. But for hole sizes greater than 8, the recommendation from DS1 is to have a higher ratio of BSR compared to traditional. What this means is the box should be between 2.5 and 3.2 times stronger than the pin. The stiffness ratio, or SR, is related to the transition between drill string cross-sections, that is the transition between the collars and pipe. Areas where this is critical are crossovers. If the transition in the crossover is great and the length is not long enough, the stiffness ratio will be too high and the structure will be at risk of failure. An example is a crossover sub that has been rethreaded multiple times. Each time the length of the sub reduces until it is beyond the safe limit for the stiffness ratio. The bottom hole assembly, or BHA, directly influences weld trajectory and load transfer. It consists of drill collars, stabilizers, heavyweight pipe, and other specialized tools. The BHA must provide sufficient weight on bit to achieve penetration, while also guiding the bit along the planned path. Designing an effective BHA requires balancing stiffness and flexibility. Too stiff a BHA resists curvature and makes directional control difficult, while too flexible a BHA may buckle or allow the bit to wander, leading to poor hole quality. Stabilizers play a critical role in providing lateral support, controlling hole angle, and preventing unwanted vibrations. The BHA also serves as the primary means of transmitting weight and torque to the bit. Drill collars supply the necessary stiffness and compressive force, while heavyweight drill pipe helps manage the transition from collars to the more flexible drill pipe. The collars are placed in the string to provide weight, but also to prevent buckling. It is essential that the neutral point is modelled to ensure that it remains within the stiff collars. If the neutral point can move up to the drill pipe or jars when the drill pipe is near vertical, the pipe will buckle catastrophically. Choosing the right type of BHA depends heavily on the inclination of the well and the drilling objectives. In low angle or near vertical wells, a stiff BHA is generally preferred. Drill collars and stabilizers arranged in a packed configuration maintain trajectory control and prevent unplanned deviations. The priority in this setting is maintaining verticality and reducing doglegs. In contrast, at high inclinations, the BHA must provide enough flexibility to steer and build angle while still delivering weight on bit. Rotary steerable systems and bent housing motors are often incorporated to achieve directional control without compromising drilling efficiency. Here, the design balances stability with the ability to adjust trajectory dynamically. The tools are lying on the low side of the hole and are supported by gravity, providing support and resisting buckling. In this situation, the neutral point can be several hundred feet along the drill string. Between low and high angles, typically in the range of 30 to 70 degrees, the challenge is achieving the right compromise. The BHA must be stiff enough to carry weight effectively, but flexible enough to follow the planned curve. In this window, stabilizer placement becomes critical, as improper spacing can lead to buckling or poor hole quality. Ultimately, selecting the BHA type involves integrating mechanical design principles with operational goals, ensuring the assembly delivers trajectory control, sufficient weight on bit, and structural stability across a variety of drilling conditions. This slide illustrates how the weight on bit changes with inclination angle. In vertical wells, nearly all of the drill string's weight can be transferred to the bit. But as inclination increases, less of that weight is effectively available because of the angle of the hole and the friction along the borehole wall. The first factor to consider is buoyancy, which is expressed as the buoyancy factor. This adjusts the effective weight of the drill string depending on mud weight. Higher mud densities reduce the apparent weight of the drill string, lowering the available weight on bit. The second factor is the inclination angle itself. As the hole deviates from vertical, only the vertical component of the string's weight can push down on the bit. This is represented by the cosine of the inclination angle. At high inclinations, the available weight on bit drops sharply. Finally, the length of the drill string section and its air weight per foot determine the baseline load that can potentially be applied. By combining these terms, we can estimate how much of the drill string's weight actually reaches the bit. This calculation is essential for planning trajectories and ensuring the bit is loaded effectively without risking buckling or poor drilling performance. The curvature index, or CI, is a comparative tool used to evaluate the severity of wellbore curvature relative to drill string performance. It quantifies how much bending stress the string will endure for a given trajectory. The higher the curvature index, the greater the likelihood of fatigue and structural failure. CI is not an absolute measure, but a way to compare different well designs or bottom hole assemblies. For example, when planning two potential well trajectories, the CI helps determine which design imposes less stress on the drill string. This makes it valuable in decision-making during the planning phase. The index incorporates dogleg severity, borehole curvature, and drill string dimensions. It helps engineers identify whether a planned trajectory falls within safe operating limits for the selected components. In practice, CI is often used alongside fatigue design criteria, ensuring that the chosen well path can be drilled without excessive risk of premature failures. Looking at the graph on the right, on the x-axis is the tension of the string, the y-axis is the curvature index, and the lines represent the different doglegs. So, if a string were in tension of 200 kips through a 10-degree dogleg, the resulting curvature index would be 8. This can then be substituted into the formula to calculate the expected number of cycles to failure of the drill pipe defined in the chart. In this case, it is 5-inch G105 drill pipe. The stability index, or SI, is a measure used to evaluate the resistance of a drill string to buckling under compressive loads. Buckling is a critical concern because once the drill string loses stability, it not only increases stresses but also reduces drilling efficiency and directional control. The SI provides a comparative assessment of how close a drill string is to instability under specific conditions. A higher SI indicates greater resistance to buckling, while a lower SI suggests that the drill string is vulnerable. Factors influencing SI include the weight on bit, the stiffness of the BHA, and the inclination of the well bore. In deviated wells, axial loads often act in combination with lateral forces, which lowers the effective stability and makes SI an essential design check. Using the SI, engineers can adjust BHA design, stabilizer placement, or weight on bit targets to avoid conditions where buckling is likely. This reduces the risk of fatigue damage and stuck pipe incidents. The graph shown has the hole size on the x-axis and the stability index on the y-axis. The different coloured lines represent the various sizes of drill collars. This graph shows that the collars need to be large to maintain a low stability index. In the example shown, a line is drawn from the hole size of 12 1/4 inches to 8-inch collars in green. Then a horizontal line is drawn to the stability index. In this case, the stability index is 170. This can be substituted into the formula to calculate the expected number of cycles to failure. In this session, we examined the key aspects of drill string design that influence performance and reliability. We began by looking at fatigue, focusing on how cyclic stresses develop and how fatigue design helps reduce the risk of failure. We then explored bending stresses in more detail, introducing concepts such as the section modulus, the bending strength ratio, and the stiffness ratio. These tools allow us to evaluate connections, which are often the weakest parts of the drill string. From there, we shifted to the bottom hole assembly, discussing how different configurations are suited to low, medium, and high angles. We explored how the available weight on bit changes with inclination and why this matters for efficient drilling. Finally, we introduced the curvature index and stability index, two practical tools that provide comparative guidance in assessing drill string performance across different well designs. Thank you for completing the sub-module. Please progress to the quiz.